6.2, regions between curves. So in this section, what we're going to be doing is we know we've been working with area between some function, we'll call it f of x, and the x-axis. So we've been trying to find this area under the curve. And remember, we've been drawing rectangles originally, and then we were trying to sum up our rectangles, and then we were trying to do that slice and sum. We're slicing it up, summing them up, and what was the total area. But in this case, we always know that the height of our function is when we plugged in some x to find the height. And then we had a width, which we were saying was delta x. So we're summing up the areas that were height times widths, and we were going from there. But the question becomes, what if now in this second picture, I have two functions, and maybe it's like this. And I want to know what is the area from A to B, but between the two curves. So it's not just between one curve and the x-axis, it's between two distinct curves. And how do I go ahead and start doing this? Well, the principle is the same. I'm still going to do the slice and sum method. I'm going to try to get these rectangles in, and I'm going to sum them up. But in this case now, my height is now going to have to be between this f of x function and this g of x function. So I'm still going to have a width that's delta x, but now in this case, my height is really f of x minus the g of x values. And I'll get that height of the rectangle, and we're still going to do the slice and sum, and we're going to go ahead and add them up. So if you notice, I'm always going to start with f of x, and we'll call this one the upper function, and g of x we'll call the lower function. So if you wanted to, you can see that we have the area of a region between two curves, and they're continuous functions where f of x is the bigger one, or the one that's always going to be the upper is greater than or equal to the lower, which makes sense, on an interval from a to b. And the area then can be written as the integral from a to b of f of x minus g of x dx. So if you wanted to, you can always think of it as the upper minus the lower function, is we're going to take the integration. So let's go ahead and do a couple of examples of those. And I have for us number 5. And we're given the function y equals x and y equals x squared minus 2. Now, if you're not sure which one's the upper or the lower, you can definitely go ahead and graph this. You don't have to, but you do have to know principles of what you're graphing. Here's the y equals x, and then if I was to graph the the x squared minus 2, I can see it would graph like that. So now I can have a better visualization of which is the upper and which is the lower. And then on this case, we need to go ahead and find the bounds. I don't know what my A and B is, but if it's going to say the area between these curves, this has got to be A where this is meeting. And at this point, this has got to be my B. So my first step is to go ahead and find my bounds of integration by setting these functions equal to each other and solving where they cross or intersect. Now, if you do have your calculator, you can do that on the calculator. But in this case, I don't have to. I can see I have a quadratic trinomial, and from here I can factor this. This is factorable. And I see that x is equal to a -1 and a +2. So those are my bounds that I'm going to use now. And then setting up my integration from -1 to 2. I can see that my linear equation x is the upper function minus my lower function dx. And if you wanted to, you can definitely neaten this up and you get x minus x squared plus 2 dx. This is easy to integrate, and then you can go ahead and find the area from here. So if we wanted to find the antiderivative, we should get 9/2 as our answer. So then this is what our process, our basic process is to find the region between two curves. So I'm going to go ahead and do one more that's a little bit on the trickier side. And this one is giving us y equals 2 over 1 plus x squared and y equals 1. So definitely, this is one you're going to want to have to try to graph to see which is the upper function. And we can see that it should graph like this. This is y equals 1. And the other one does graph, whoops, like this. And it graphs like that. So if I want to find the region between these two, we know we're trying to find this almost triangle. It's not really quite a triangle. And we're going to find that area. So the biggest question is you have to know where they intersect. And if you want to go ahead and set it equal to 0, or set them equal to each other, or put it in your solver in the calculator, graph them and find the points of intersection. We do find that the x values where they cross are plus and minus, or positive and negative 1. So from here, I'm definitely going to go ahead, set up my integration from negative 1 to 1, and I see that the function 2 over 1 plus x squared is the upper function. And then I'm going to go ahead and find my antiderivative. It should be 2 tangent inverse of x minus x. And we're going to evaluate it from negative 1 to 1. Now at this point, if you're going to go ahead and plug it in your calculator and get a decimal approximation, that to me is fine at this point. But if you do it, leaving it exact, you should end up with pi minus 2. So either answer for me is fine. You know, in the textbook, they're going to leave it in the exact form. So next, I want to move on to something called compound region. Compound region is when we have problems, like maybe I have some issues where I'm going to have to break up our integration so that it's easier to do. So I want to do example number 16. Because I'm given the function y equals sine x and y equals sine of 2x. And on the interval from 0 to pi. So they're telling us our integration already, but, our bounds for integration. But if I go to graph this very loosely, I get sine, and then I'm going to get sine of 2x. So my problem becomes I have this area, and this is a very loose sketch of what it should be. It's not quite exact, but my key is to show you there's two problems. Which one is my upper and which one is my lower? So if we said once again, if this is the 2x, notice at one point on this interval here, it's below, but on this interval here, it's above. So my function changes where it is, our upper or lower function. So I'm definitely going to want to do this as a compound region and split this up. We'll call this A, we'll call pi B, and we'll call this point C. So we're going to have to definitely find the points of intersection here in this middle part. So we're going to go ahead and split this up, and we see here if this first one, sine x, Uh-oh, and I drew my graph wrong. Sine 2x should be the first one, minus sine x dx plus, and then I have my other one where the sine x minus sine 2x dx. So now I know we're going from 0 to pi. It's that point in between that I have to find where they intersect. And it turns out that should be pi over 3. So that's what I'm going to have here and here. And then when you go to calculate, you should go ahead. I get that this first interval for integration should be a quarter, and the second interval for integration should be 2.25, and I get a total of 2.5 or 5 halves. So either way you could do this, but the key is at this point you may have a compound area that you're going to have to split your integration. So I want to move on, and we're going to talk about now, what if I have a graph where the functions are like this? And I want to go ahead and evaluate this area. So it's not an upper or lower function. Or what if I have a graph that slightly looks like this? And I want to evaluate this area. Or what if I have a function that was something like a sideways parabola, but then I had something else, maybe some kind of cubic function, and I want this area. How do I find these areas? Well, if I can't do vertical, in a sense, my rectangles are vertical, I'm going to go ahead and try to evaluate these with my rectangles in a horizontal fashion. Instead of A to B, we're going to call this point C and this point D. Same thing here, this would be C and this would be D. Same thing here, this would be C, this would be D. I still have a lower and upper bound, but in this case now, this is going to be in terms of y. So what I have here, we'll call this function f of y, where x equals this function, and this one to the left, we'll call it x equals g of y. And in this case, I'm going to still do my subtraction between the two functions, but I'm going to always be doing right minus left. So we call this in terms of y, or respect to y. So we have here that f of y is the greater function than the g of y, or you can think of it as the right function and the left function. So now we're always going to be doing right minus the left when we set up our integration. And we're going to be going from the interval C to D. So we always have a lower and upper bound still. So let's go ahead and try a couple of examples of this. We're going to do number 23. We're given a picture, and it tells us that this function is x equals 2y squared minus 2, and this one is x equals negative y squared plus 1. And actually, that's not what they give us in the picture. They ended up really giving us in y equals form. And because I see I don't have an upper and lower, I have a left-right situation, I went ahead and took the equations and solved for x, because I need these functions in terms of y in order to set up my integration. So from here, I can see right now that this is going to be my y equals 0 is going to be my lower bound, or my c, and I had to set these equal to find out where they were going to be crossing up here for my upper bound, and it turns out that d equaled 1. So my integration with respect to y is from 0 to 1, and I'm going to be doing the right function minus the left function. Oops, got an extra. And then from in here, you want to go ahead and simplify this so we can integrate it easily. I get a negative 3y squared plus 3 dy. So everything's in respect to y. And then you find your antiderivative, and we're going to evaluate. And we see that it's an area of 2. So same thing here. If you want to process the same way, except when you don't have an upper or lower, think right and left. So we're going to go ahead and I want to do one more. And we're going to go ahead and the last couple problems for the homework will be just setting it up either in terms of x, where you might have to do a compound region, and showing, for example, how to do it in terms of y. You don't have to evaluate the integration, but you just have to set them up. So we're going to do 27. All right. We're given this picture. And this is the area that they want us to find. In this case, I don't have an upper or lower. I'm going to have to do this in terms of y. So they gave us that this is y equals x, and they gave us that this function is y equals x squared minus 2. So the first thing I'm going to want to do is find where they cross, and then I'm going to set up my equation. They said do A as in terms of x. So we're going to say that I found where it crosses the x-axis, and it turns out that this function, when we solve for x when y is 0, will be negative square root of 2. And then I try to find what this point is here. And then I'm going to go ahead, in this case, it's going to be negative 1 when I solve for that. And that is going to be, if I do this case, an upper and lower, it's basically going to be the 2 minus the x squared, or the x squared minus 2. Oops, I'm sorry. 2 minus the x squared dx plus the negative 1 to 0, and that goes from the c to this point here. And we're going to do the other part, which is the negative x dx. We're doing this because of where we are below, we're reverse of what we're doing. If we're above the x-axis, we're below the x-axis. This is keeping it in terms of x, and I had to do it as a compound region. Then they said, okay, go ahead and do this, set it up where it's in terms of y. So I'm going to go ahead and just say that I can do the entire region then in terms of y, finding this value and this value. Turns out the point of intersection of those two functions is negative 1, and we're going to be going up to the x-axis, so we have a bound of 0. And then we're going to do a right minus left. And then from here we can, all they wanted it for us was to go ahead and set up those integrations, not to evaluate.